We can hear you. Yes, thank you.
Very nice. Okay, does everyone see my screen?
Yep.
Perfect. Let me see if I can full screen this. Okay. This is as full screen as it gets. Okay, so I'll be doing a presentation on how we can use Python for generating FMUs. So it's really ideal for prototyping things and kind of gluing together other FMUs we have if we want to do something a bit more exotic. Yeah, so really the vision of the FMI standard is to enable co-simulation of models created by different tools. And the mantra is that we can use a tool that is highly specialized for doing this, like modeling a particular part of a system. So this is what I've tried to show here. We have different tools that are really good for modeling a specific domain. So we have something like Simulink or 20sim, which is really good for modeling discrete continuous dynamics, whereas something like Overture or System C would be more suitable for modeling discrete systems, so things like controllers in our system. The issue is that sometimes we have the need for something that kind of lies in between, something more general. Yeah, so things like doing live logging, user interfaces. If we want to create an adapter to some outside environment, this could be robotics operating system, Unity. If we want to do some adaptive algorithm, it would be nice if we could use a lot of libraries for this. And in general, as Nick kind of showed, it's very difficult to write a FMU from scratch. It's very difficult to get this right. So we want to avoid this. So really, it should be accessible. So we don't want to bother with learning some specific language every time we have to do a model. We'd like to avoid doing compilation to a lot of different targets. It would be very nice if we could do this quickly. So if we can reuse a lot of libraries, that would be really nice. And it needs to be expressive enough. So we need to be able to create these sort of exotic FMUs that we otherwise wouldn't be able to do. And also, again, it's very hard to get the compliance right. So we want to automate the generation of the model descriptions. And our solution to this is basically to write FMUs in Python. As you probably know, it's a very popular language. It's arguably one of the most popular languages in the world right now. It has more than 200,000 libraries available, including numerical solvers, machine learning libraries. So there's really, if you have a problem, there's likely someone who has already solved it for you. And again, it's a general purpose programming language. So you get the specialization for a specific domain, like solving ordinary differential equations through libraries, not through the language itself. And let's go on to the demo. I've recorded this because I know that I'd otherwise mess up. I'll just pause it at a specific moment. So the tool itself is a command line tool that can be used to generate FMUs and to export them sort of as finalized FMU archives. So the first command you'd use is generate. The tool itself is called PyFMU. So here I'll try to create a sine wave generator. So you specify its name, you specify where it should be stored, and that generates the file up here. And as you can see, it's created a small configuration file specifying that there's a script called generator.py, and that contains a class named generator, which will be used as our FMU instance. Now, initially, it will create a sort of a template. This is a 2-input adder, so we'll just add 2 numbers together. And what you saw there is I ran the debug on the script to make sure that everything is correct. So there's a small test case built into the template that is generated. Okay, so let's wait a moment, then you'll see. So the idea is that the slave class, so the FMU is really valid Python code. It's just being sort of wrapped in a sophisticated way. So what I'm doing now is I'm just adding variables to the model itself, and later I'll show how we kind of expose these in the model itself, so we can use it in a co-simulation context. So this is what I'm doing with the register parameter. This is registering, adding this parameter into the output. I'm declaring that there's something called f. It has type real. It is of a variability fixed, and I'm now giving it a description. So when you generate the model description, it's not just F. You will actually see the description that is saying that it's the frequency of the model. Okay, and this is, of course, the amplitude in the phase. And then finally, I register an output called Y. And the nice thing is that you can use, Python's intelligence to give you suggestions. So everything you're doing here, you're really using all of Python tools, because this is something like getting tooling on the level of a big programming language like Python is really difficult. It's a very time-consuming job. So what I'm doing now is I recognize that the output only depends on time. So if I just update in these are the FMI functions: setup, experiment, reset, do step. These would be called when the corresponding function, the FMI interface, is called. So you just do whatever you want, and you only need to implement the ones that you need. So the rest you can just remove, as I did earlier in the example. And now I implement the output, and you can use Python properties for this, because Python has a very sort of dynamical structure to the language, so you can implement sort of attributes in multiple ways, including as properties like this. And of course, I need to import the math library. And what I'm doing now is I'm importing a plotting library because I want to first check in Python if this FMU is correct, because this can save us a lot of time, so we don't have to import it into a tool to co-simulate it and then recognize that something is wrong and having to trace back this. It's much easier to do with a debugger. And this is what I'm doing. I'm plotting the time and the Y variables. I'm simulating from 1 to, I think, I'll write 10 seconds. And what we see is a sine wave, and this oscillates 1.5 times or something like this. Now it's only kind of showing Python code. So the next thing I'll show is how quickly we can get this into an FMU. So this is the export command. So we specify the name of the project, the output directory. So I'll just store it somewhere else so I don't overwrite the project itself. I will see that we have something called exported generator. And in here, I'll just freeze it. You can see that this is all the stuff we'd have to write by hand if we were implementing this from scratch. And as Nick said, it's very hard to get this right, especially if you're using some of the more specific features of the FMI specification. So all of this is done dynamically, and by generating this from the code itself, then you're assured that there's consistency between the two things. There's no risk of this being sort of outdated. And we see that in here, what we do is basically we just copy over the script. And we also just have these two binaries which are pre-compiled, so there's no compilation involved when you're exporting the FMU. It's entirely generic. What I'll do now is I'll open a simulation tool called FMPy, because it's very easy to do. And I'll just show you how the simulation of the exported FMU looks like. This doesn't show us much, so we'll just increase the simulation time to 10 seconds instead. And try increasing the frequency to 3 times as much, and we see that it oscillates faster. So this is kind of how you can create a very simple toy example of an FMU using PyFMU. Peter, how are we with time now?
Well, there's like 4 minutes before Casper should be on.
Okay, I think we can make it then. Okay, I'll show. I have a small demo made by another master student at Aarhus University. So basically, what this example shows is that you read a image using a image processing framework, and then you, based on this, you create a sort of map of obstacles, and then you live plot the trajectory of a robot. So this is what is shown here, and this is all made in PyFMU. So you can see these indicate the obstacles here. So this is just showing you can use it for things such as live plotting, which is really useful for long running simulations. If you look into CPS, you have like standard plotting functionality, but not something like this. Okay. So I think we've already seen this, but inside of an FMU is really just a zip archive with binaries for every platform, and then you have a model description. So the binaries is kind of what implements the behavior of the FMU, and the model description is what declares the inputs, the output, the parameters. So internally what happens is that there's this precompiled DLL that you just get for free with the tool. And when you call instantiate on this, it will have a look in this slave configuration file we saw earlier, and it will recognize that it should load some class, in this case generator from generator.py, and that will be loaded into a Python interpreter, and then do step and stuff like this will be forwarded to this instance of the object. And essentially how the model generator, so the model description is generated is that there's a command line utility that the export command line utility, it loops over these variables that you declare inside Python itself, and it just creates these things. It's quite trivial to do because it's already in Python. And the way that I've ensured the consistency of this model description is basically run as many tools as possible. Reading the FMI standard is not sufficient to understand how it should work. It's really about maximizing the compatibility. And this is the easiest way to do this is just to pass it through a lot of tools. So I'm passing it through Nick's VDM check and using the FMU compliance checker Nick also talked about. I loaded into Maestro, and I also simulated using FMPy. So this is really the setup for this. And as I showed you earlier, the nice thing is that you can use all the Python tools. So traditionally, you would have to change the model, export it as an FMU, import it into your tool, run a code simulation, and then you would have to sift through a lot of log messages to see what happened, what is wrong. Using PyFMU, it's in most cases a lot simpler. You just debug the Python code itself. So if it's sort of issues with the specific FMU, you can just use the debugger. Write a small test setup like this, load a trace of the input and the expected output, and you can compare these. Yeah, future work, there's still parts of the standard which are not implemented, like derivatives and units. It's relatively easy to implement this. It's just limited time. And then in the future, we would like to also support FMI3. And I think if we have more time, questions, otherwise there's links in the presentation to the GitHub repository in the chat.
We have time for a quick question if we have any questions.
I have 2 questions. Do you support units?
This was what I didn't show before, okay. but it should be relatively easy to do. So I imagine what we will just do is when you register. So when we go in here, we would probably just add something like unit equals, and then perhaps a string, something like this. Okay. And this should be, I mean, it's just Python code, so it's easy to do. It's the easiest place to do it. So it can definitely be supported if we need it.
And I guess you could also have a general framework for serialization of FMU state.
Yes,
that you
indeed.
Can put in all these.
Yes, okay. There is a thing called Pickle.
Okay.
You can just use that, so it would be trivial to do so.
Yep. Okay. Thanks.
Perfect. Thank you. So Casper, maybe you can take the screen. Maybe you need to de-share. Yeah, Casper's there.